Welcome to The Explainer. Today, we're going to do a real deep dive, focusing on just one single GCSE Physics question, question 05. We're going to pick it apart piece by piece and show you exactly how to lock in every single available mark.
Okay, let's just jump right in. Have a look at this graph. Now, I know it might just look like a bunch of dots in a line, but this data, well, it tells a pretty profound story. This is the actual evidence that underpins the Big Bang Theory, one of the most important ideas in all of science.
And our mission here is to show you how to read it like an expert. We're going to use the exact language from the mark scheme, because that's what gets you the credit for what you know. The goal is simple, a perfect score on this question. Let's do it. So the question starts off by testing the absolute fundamentals. You can think of these first few marks as a quick check to see if you have the core definitions completely locked down.
First up, 05.1, and it's a classic fill-in-the-blank. The term redshift describes the observed increase in the what of the light from a distant galaxy. It's asking for one very specific property of light. What is it?
And the answer is wavelength. That's it. That's the one precise word the mark scheme is looking for. When a galaxy is moving away from us, its light waves literally get stretched out, which means their wavelength increases. Okay, moving on. Question 5.2 asks for another one of these foundational definitions. How does the Big Bang Theory describe the universe when it began? Now, for the full mark, you absolutely need two key ideas here. The mark scheme specifies that the universe began as very hot and very dense. You've got to include both of those to get the point. All right, so with those definitions covered, the question now shifts gears. We're moving into data analysis. It's time to actually pull out the evidence that's hidden in plain sight right there in the graph. So, back to the graph. Whenever you see one of these, the first thing you should do is understand the axes. The x-axis, the one along the bottom, represents a galaxy's distance from Earth. The y-axis, going up the side, shows its speed. So, simply put, we're looking at distance versus speed. Now for question 05.3. It asks you to simply describe the relationship. Notice that word describe. It's not asking for an explanation yet, just a description of the pattern that you can see in all those data points.
The clearest answer, and this is straight out of the mark scheme, is the further away a galaxy is, the faster it is moving away. You could also say that speed is directly proportional to distance. Either of those simple, direct statements nails it and gets you the mark.
Next up, 05.4 is a multiple choice question that's really just checking if you know your standard form and your prefixes. Which of the following is the same as 6 times 10 to the 12 terameters? The whole key here is knowing what tera actually stands for. So, the prefix tera means 10 to the power of 12. That means you're calculating 6 times 10 to the 12th multiplied by another 10 to the 12th. And if you remember your laws of indices, you just add the powers. 12 plus 12 gives you 24. So the answer is 6 times 10 to the power of 24 meters. It's another straightforward mark, but only if you know your prefixes. Okay, now this next one is where it gets really interesting. This is a 2-mark question that requires you to connect the data directly to the theory. Explain how the data in Figure 9 supports the suggestion that the universe began from a very small region.
Because this is a 2-mark question, you need a 2-part answer. Step 1, state the evidence from the graph again. The further away a galaxy is, the faster it moves away. Step 2, explain the implication. If everything is moving apart from everything else, then if you rewind time, it must have all started from a single common point. Evidence plus implication equals 2 marks. Simple as that.
All right, let's move on to the final part of this question, because science doesn't just stand still, right? This section is all about how theories have to evolve when new, unexpected evidence comes along.
So, question 05.6 adds a modern twist. The original Big Bang Theory kind of suggested that gravity would eventually slow the expansion down, but new data says the opposite. So what does it mean if distant galaxies are moving away even faster than we thought? The answer is simple and direct. The expansion of the universe is accelerating. That's your 1-mark answer. And this observation was a huge shock to astronomers. It actually led to new theories about a mysterious force called dark energy that might be pushing everything apart. Now, when a massive claim like that is made, it can't just be accepted. And that leads us perfectly into 05.7, which tests your understanding of the scientific process itself. Give one reason why peer review is an important process. And the mark scheme gives you a couple of good options here.
You can say it's to check for validity, to make sure the methods were sound and the data is reliable, or you could say it's to prevent false claims. Both get at the same core idea. Peer review is basically science's quality control mechanism.
And for the final question, 5.8, they give you a fantastic counterexample. Almost all galaxies are redshifted, but our cosmic neighbor, Andromeda, is actually moving towards us. So how does that change the light we see? You need to describe the changes to both wavelength and frequency.
Well, this is the exact opposite of redshift. It's a phenomenon called blue shift. As Andromeda rushes towards us, its light waves get compressed, all squished together. So for 2 marks, you need 2 points. First, the wavelength has decreased. Second, since frequency and wavelength are inversely proportional, the frequency has increased. So wavelength gets shorter, frequency gets higher. That's blue shift.
So, let's just recap the skills that you needed to absolutely nail that question. We had to define terms with total precision, we had to describe a graphical relationship clearly, we had to build a logical 2-step explanation, show we understand the scientific process, and finally apply all that knowledge to a totally new scenario.
And really, this whole thing just brilliantly illustrates that science is a living, breathing process, not just a bunch of facts in a book. Which leaves us with a final thought to chew on. If new observations could so radically change our understanding of the entire cosmos, what accepted theory that we hold today might be completely rewritten by the data we collect tomorrow? Thanks for joining us on The Explainer.